Okay, everyone. Today I'm going to talk about session 4.2, Math 180, calculus business. Um, so in this session, we're going to talk about the natural logarithm function. Before we start to get in this session, I would like to remind you some information from the correct algebra. First thing, the logarithm function is in the form as log base b of x equal to y. So this is a logarithm function, okay, and it can be rewrite as the exponential function by you just gonna change the base. So you're gonna put the base b, now it's base b, okay, raised to raised to raised to y, okay, and equal to the argument inside the log, which is equal to x in this case. All right. So this is a definition of the logarithm, and I mean, like, if you still like don't know what does it mean of the log, so I'm gonna say the log mean that what is um, what is the power of uh, what is power of base b to get to x, something like that. All right. Um, um, and now one more thing that you need to remember is for the logs base with the number e or natural number of x, you can write it as ln x, or it's called natural log x. Okay, so it looks like there is no base e or hidden base e, and instead of write out log, it's write at ln x. Okay, so remember that if I write ln x, it means log base e of x. Okay, so now let me go ahead and get into 4.2 today. First, we're gonna have the first form of the natural logarithm. So in the equation a equal to e over t, the number t that when used as an exponent on the base e produce the number a is called natural logarithm of a. Okay. So so that's the reason why you can just rewrite this as ln a equal to t, right? You can see that. Okay, so then you can see if a equal to et, then t gonna be equal to ln a in here. Now, and the final form gonna give me the conclusion that if I have t equal to ln a, then I can reverse it to be exponential form, or in another way, I can change it to be log form. And in here, I have exponential form is a equal to e to the power t, right? So know that sin t is a log and an exponent, right? Logarithm exponent. You have to know that. Okay. uh, and t equal to ln a if and only if a equal to et. So this is exactly the definition of natural log or final form of the log. And note number 3 we view that e to t is always positive number. Okay, so that's a equal e to t is also is give me a is always positive. Okay, so I gotta say a is always positive. Can it be equal 0? No, it cannot, right? So, because e to t will never become 0. So and what else? What else I need to tell? And the argument of the natural log must always be positive. Be, uh, uh, yeah, because a is always greater than 0. So if I have like ln of b ln base b of x, then x in here has to be greater than 0. Okay, all the argument always has to be greater than 0. Okay, and the last one is t equals to ln a's expresses t as a function of a, since for each value of a, ln a produce exactly one value of t. Okay. Now let's do an example. Some example. Okay. So in example 1 here, I want to express the equation in logarithmic form. Okay. So I am now having exponential form. So I'm going to change it to be logarithmic form. Okay. So I would like to see. I would like to ask you what is base in exponential form in here. Everyone should know that base in here is e, right? And then the power in here, the also exponent in here is 2x. Okay. So I would like to write as ln of y, because base is e already, and the argument should be y, and it should be equal to the exponent, right? Because you have to remember that the logarithm are exponent. Okay, the logarithm is exponent. Okay, so remember that. And now, similarly, for problem B, you can pause my video for 1 minute and try to do it by yourself. But I will give you the answer now. It's going to be ln, because the base in here is e, right? So ln of 20, okay, equal to exponent, okay, which is negative 0.3x, okay? Okay, let's move on. Example 2. I want to convert each log equation to the corresponding exponential equation. Okay, so this will be easy one, because what? From the definition of the log, you can easily say that base here raised to 5, right? Raised to and equal to the argument, right? So again, I'm gonna write it as e to the power 5 equal to 7x. Okay. Now let's move to B. Similarly, you will have base E raised to negative 0.01, right? Equal to x plus 8 equal to argument, right? So I'm gonna have E to negative 0.01 equal to x plus 8, right? Okay, so that's the answer. And now let's do an example 3. We asking you to evaluate some logarithmic function, logarithm function, expression actually. In here, I have ln e. What is that equal to? So I go say, let's make it equal to question mark, right? Or I can even write as a variable, say it's x, and I'm looking for the x. Okay, so I will change. Okay, I will change the ln e become ln equal to x become an exponential function or exponential form. Okay, so it's going to be base e raised to x. Okay, equal to e, right? Base e raised to x equal to e, and in here this e is power 1, right? So see, base are the same. Now you can just let the exponent equal each other. I have x equal to 1. Okay, so then the value of ln e will be equal to 1, and that should be one of the properties of natural log that we need to use for this section later. Okay, so I put a start for this. And now let's move to B. Similarly, I'm gonna put ln1 equal to y, and then I'm gonna change it to be exponential form as e to power y equal to 1, right? And then I'm gonna change 1 to become base e to power something. So e power y equal to e e to power 0 will, I mean, anything power 0 will be equal to 1. So I'm gonna put e to power 0, okay? And then since base are the same, then the exponent has to be the same. And in this case, y has to be equal to 0, okay? And if you remember in the college algebra, you have learned that log of anything, say log of log base x or base b of 1 will always equal to 0. Okay, so log base of anything that of 1 will always equal to 1. Similarly, in here, log base e will always equal to 1. If the argument equal will always equal to 0 if argument equal to 1. Okay. Let me say yes, note. Okay. Now, so then I'm gonna make a conclusion that ln of 1 will always equal to 0, and this also properties of natural log that we will use for this section. Okay. Now, let's come to properties of natural log. So I have totally 6 properties that you need to use for natural log. These 2 you have learned from, I have derived from the example 3 above, and for number 3 here, you can easily derive um, by ln by z equal attribute. I mean, this is easily to derive if you can you change it to be exponential form, and it's the same thing with the example 3. You're gonna find it equal to x later. So there's no deal for this, okay? And also, if you remove from the correct algebra, you see that's log of log space b b to power something, say a, okay, then it will be equal to a, uh, because you have to know that log is uh, log, the logarithmic is exponent. So in here is exponent of b to get ba, gonna be a easily. It's just exactly the definition. Okay, so similarly with the area ex, it's gonna be equal to x. Now these three properties is very important. Okay, why? I'm gonna say this help you um, to expand. Okay, to expand or extend. Okay, expand the lock. Expand the lock by the from the left to the right way. Okay, and so you see like in the fourth, you see that the multiplication inside of the argument here will change it to be two addition of the log, right? So from one single log change to be two log, two addition log. Okay, so it extend out like that. Um, and um, similarly for 5 and 6 here, 5 is a change from the division to be subtraction, and exponentiation and become multiplication. And remember that the exponent in the argument of the log will move to the front of the log, and to be like a multiplication between a constant with a log. Okay, so this also an expand of the log. Okay, so remember, if I ask you about expand the log, then you always go from the right to from the left to the right. Okay. In another way, if I ask you to condense, okay, condense or um, write it into a single into a single block, then you want to go from the right to the left in these three forms. Okay. Okay, let's apply this in example 4. So in example 4, I have ln of 3x, and I want to expand this. Okay, so if I want to expand this, I have to look at the three properties, the last three properties from 4 to 6, right? And I want to go from the left to the right. Okay, so in here, I notice that argument is 3 times x, which is a multiplication. So I'm gonna change it. I'm gonna change it to be 2 addition log. So it's gonna be ln of 3, okay, plus ln of x. So see that. So in here, I know that it is like a two factor inside of the argument, which is 3 and x. So I'm gonna just change it to be ln 3 plus ln x. Okay, so no doubt for this. Let's move to B. B is more complicated, but if you try to make it like from general first and then go to detail for each, it should be okay. So look globally, you see that this like the argument look like a what, like a fraction, okay, like a rational. So you need to think it is a division, okay, and since a division, you want to look back the fifth properties. Okay, number 5 here, which is this which is a division, become a subtraction. So I'm gonna change. It's become ln of the top. Okay, the whole top is ax squared, right? And minus for ln of the whole bottom is x plus 4. Okay, so now I'm gonna try to thinking, can I expand more? So look back each term here. For the first term, I noted that there is still there is like a there is some factor inside of the argument, or there is multiplication inside of the argument for the first term, and I can rewrite it as ln of 8 plus ln of x squared, and I'm gonna minus for ln of x plus 4. Okay, I cannot change for the second term, because why? Because it doesn't have anything to change. It have x plus 4, but I cannot change that. I cannot split it. Okay, so let me change the color a little bit. So in here you see that there is one natural log that have argument with the power. So I'm gonna think about the sixth property that have exponent inside of the argument. So I will change it to be 2 ln of x, right? Because why? Because it is because the power when I move to the front of the ln x. So I'm gonna keep other and 8 plus 2 ln x and minus ln x plus 4. Okay, so this could be the answer already. You can expand more by split the 8, but I mean you don't have to me. Okay, so I can, I mean if you like you can expand it like okay, so it is 8 gonna be, I can rewrite 8, it become 2 to the power 3, and I change it become 3 ln 2 plus 2 ln x minus ln of x plus 4, and this should be the answer. Okay, but usually for the constant argument, I don't wanna care about that. Okay, you can, because why? Because you can use a calculator to simplify it. Okay, so let's move to example 5. In example 5, I want you to write each log expression as an expression with a single log, or I want you to condemn it. Okay, so for problem A here, I know that it have two, I mean, it have an addition between two natural log. Okay, so I'm gonna think about maybe I'm gonna apply probably 4, but look at the second term here. I noticed that there is a 6 in front of natural log. Okay, so I need to move it somewhere to somewhere in order to make it completely just natural log, and then I can combine it. Okay, so in order to to move number 6 there, you have to think about the 6 body here. That's you can move the leading coefficient to the exponent of the argument. Okay, so remember that in this case, because it's condensed, then you try to use from the right hand side. Okay, from the right hand side to the um, left hand side. Okay, and now let me do it. So first term we keep it the same as ln x. The second term I'm gonna move the 6 to be the power of the y, which is ln y6. Okay, so now it's look like I have addition between 2 ln. Okay, so now I will apply poly 4, and that's gonna give me one single ln with one argument as x times y to the power 6. Okay, because it's addition, then it is multiplication between 2 arguments. Okay, so let's move to the b. Problem b is more simple than a, I believe, but it have 3 terms. Okay, since it have 3 terms, you can just you can just go from the left to the right. What you do is you just gonna do a subtraction between 2 first term. So what you're not gonna have, it's gonna be ln. You combine that. Look at the fifth police. You have subtraction. Okay, you want to change it, become division, right? So ln of the top one gonna be a, and the bottom of the fraction is gonna be b. Okay, because I subtract for that, right? Then I subtract for ln of c. Okay, keep moving. So I will have equal to ln of a over b, everything over c. Okay, it's look complicated now, I know, but if you carefully consider each fraction here, each bar fraction here is like a division, right? So if you have like a over b divided by c, you can change it to be a over b multiply, let me write this over here, a over b multiplied by the reciprocal of c, which is 1 over c, and then you're gonna have equal to a over b times c. So you can change this, become ln of a over b times c. Okay, so that's be the answer. Now I'm gonna talk about the reversal effect of natural exponential and natural logarithmic function on each other. So in example 6, I would like to approximate the solution to the equation e to the power 2x plus 5 equal to 12 in 4 decimal place. Okay, so how can I do this one? First thing, I would like to let's see. I would like to change this to be uh, logarithmic form. So I'm gonna change it to be log form as ln base 12, okay, equal to the exponent, which is 2x plus 5, okay, all right. And and in order to and remember that if you see the variable in the power and you want to solve it, you have to change the form to be log form, okay? So for later, there is some problem that you need to use this, okay? So now I need to isolate the x alone because I want to solve for x, right? So I'm going to subtract both sides by 5. I will have ln 12 minus 5 equal to 2 of x, right? And I will divide it by 2 both hand side to get the x alone. So I have x equal to ln 12 minus 5 divided by 2, okay? Okay, so now this should be the time that you need to use the calculator. Let me see. So I use my calculator. Here we go. So I'm using TI-83 here. You can use LN by using the button here, okay? LN of 12, okay? And then a minus for the 5. Okay, so this is the top. If you write where it said divide by 2, that is wrong. So you have to put enter, and you get negative 2.515. Then you divide it by 2 now. So then it's going to be equal to negative 1.257. And because it's a they want to have 4 decimal place, then I'm gonna route it to 4 decimal place, which is negative 1.2575. So x will be equal to negative 1.2575. Is that correct? Yeah. I'm gonna change it approximately. Okay. So this gonna be the answer. Okay. So last example. Okay. So in example 7 here, let's read it. The radioactive isotope uranium and 235, okay, decay according to the exponential decay model. A equal to A0 e to the power negative kt, where A0 is the amount of 235 uranium initially present. Okay, so A0 is initially present, okay, or amount initially, I'm gonna say that. And A is amount present after T million t million years. Okay? So in here, t is a million of year units, okay, not year. And k is decay rate. Okay. All right. So in problem A, the half-life of 235 uranium is about 700 million years. Use this information to calculate the value of decay constant for this model. Okay, so in here, let me say solution. Okay. So in this problem, in this part A is tell you the information is tell you that the half-life of uranium is about 700 million years. So what does that mean? So like A, after 700 years, uh, um, so I'm gonna say at t equal to 700, right? A, the amount present A will be just a half of the initial amount of uranium, okay? So I will substitute to this information into the formula. So substitute into A equal to A0 E to KT. Okay, I substitute all this information into this equation. So what do I have? So now I'm gonna have A equal to 1/2 of A0. So I have 1/2. Let me use it. Okay. So 1/2 A. I need to have. Excuse me. Okay. A0 equal to another A0. Copy this. E for negative. Okay, so E power negative K T. T in here is what? 700. Okay. So now time to do calculation for this. So I'm gonna divide both sides by A0 to see what happened, right? So I will get rid of A0. So remember that I divide both inside by A0. I will have so I will cancel A0 both inside, right? So now I have e to the power negative k. I'm gonna change this become negative 700 k. Because it's multiplication. All right, equal to 1/2. So in this case, I want to, because I'm looking for k. What is that equal to? And k now is in the exponent. Okay, the variable is in the exponent of the e. So what I need to do is I need to convert it to be the log form. Okay, so what is that going to be? The log or the log base e, which is ln ln of 1/2. So let me copy this. So ln of 1/2 going to be equal to negative 700k, right? So negative 700k. Okay. So now I did put down negative 700k to put out. So then I can now solve for k easily. I need to divide both hand side by 700. Okay, so I'm gonna have k. I mean ln. Okay, let me write this guy. So I'm gonna have ln 1/2 divided by negative 700 equal to k. Okay, I divide both hand side by negative 700. Okay, so in this case, you need to use a calculator. So you're gonna have ln of this ln of 1 divided by 2, and then divided by negative 700. Oh, I only did 1. Okay, so enter. I have an e, that means 10 to power negative 4. Okay, so I need to write as k gonna be equal to what I should do. How about I gonna click this to see? They don't want to give me. Oh, okay. So I would like to click it. Okay. So I'm gonna have 9.9. And they want me to write it in. They don't tell me what decimal number they need. I can just use. Let me see. I can just use 2 significant digits. So it's gonna be 9.9 times 10 to the power 94, which is approximately 0.00099. Okay, so 1, 2, 3, 4. Okay, yeah. So this is gonna be the answer. Oh, it should be negative. Oh, should be. Let me see. Let me check. Okay, so it's not. So this should be the answer. Okay. And now let's move to B. So for B, use the model with newly calculate value of k. So I have k already to determine how many years it would take for a particular quantity use uranium to decay to 90% of its original amount. So in here, they've given you that A will be equal to let me see, decay to 90%. Okay, so A is going to be equal to 0.90 at the A0 initial amount. Okay, and the other information is K equal to 0.00099. Okay. What else do I have? And they want me to find t equal to what? Okay, so now let me substitute into equal to 0 e to power negative kt, right? So I can have so now A can be 0.9080, okay, equal to A sub 0 times E to negative K is 0.00099 T, okay, and now I'm gonna just divide both inside by A sub 0 to get A 0.90 the left equal to E. I'm gonna copy this down. Okay, E to the power negative 0.00099 T. Okay, so in order to find T, and T now is in the exponent, so I need to put it out by convert it to ln form, convert it to natural log form. So let's convert it. I'm gonna have ln 0. Okay, 0.90 equal to the power, who is negative 0.00099 t, and that's gonna give me any variable inside. So I'm gonna have this one. I'm gonna have top is ln of 0.90, bottom is negative 0.00099, and that's equal to t. Okay, so then t had to be equal to so let's make using calculator, say ln ln 0.90 divided by negative 0.00099. That's gonna give me the answer as 106.4. So yeah, I'm gonna say 106.4 million years. Okay, that should be the answer. And I would like to make a conclusion that we can conclude that after approximately 106.4 million years, a quantity of 235 uranium will have decayed so that only 90% remains. Okay, so I have covered session 4.2 today. Uh, I will see you in 1.4 next time. Don't forget to do XYZ homework and your assignment 4.2. See you next time. Bye.